Hi, I want to use Bohr's hydrogen model to calculate the frequencies and wavelengths of the four visible lines that we get in the Balmer series for excited hydrogen. Now, from Bohr's hydrogen model, we end up getting quantized energy states, where the energy of each state is equal to negative 13.606 electron volts divided by an integer n squared. So, to make our lives easy, I want to start by calculating all of the energy levels that we're going to need. Now, the lowest energy level, or ground state, for a hydrogen atom would be n equals 1, so that would give us an energy level of negative 13.606 eV. My next energy level, which is the bottom level in the Balmer series, where if we're emitting light, the electrons in higher orbits would be dropping to, the energy of the second orbit is going to be negative 13.606 electron volts divided by 2 squared, which is divided by 4, so that would give me negative 3.402 eV. For the n equals 3 energy level, I'd divide 13.606 eV by 9, and that gives me an energy of negative 1.512 eV. For the fourth, fifth, and sixth energy levels, we would be dividing by 16, 25, and 36 respectively, and that gives us energies of negative 0.850 eV, negative 5.44 eV, and negative 0.378 eV. So the lines that we see in the Balmer series are a line that happens to be almost in the ultraviolet end of the spectrum, a line that looks like a really dark blue, a kind of tealish, like blue-green line, and then a very strong red line. Now, those lines correspond to n equals 6 transitioning to the n equals 2 level, n equals 5 to n equals 2, n equals 4 to n equals 2, and n equals 3 to n equals 2. So let's calculate the frequency and wavelength for those lines for the Balmer series. So the first thing we need to do is look at the energy of the orbit transition. So we're ending in orbit 2, we're starting in orbit 6, so I'd take energy in level 2, negative 3.402 eV, I'd subtract the energy in level 6, negative 0.378 eV, and that gives me an energy of transition of negative 3.024 eV. A negative sign in this transition energy means we're releasing light. A positive sign would mean we would have to be absorbing light. And in absorbing light, you take electrons from low energy levels and you raise them to a higher energy level. And the reverse process has the same frequency, it's just taking the light in rather than giving the light off. So 3.024 eV would be an energy of negative 4.84 times 10 to the negative 19 joules, converting from eV. So to find frequency, we can use the Planck energy relationship, E equals hf. So my frequency would be my energy in joules divided by Planck's constant. So if I take 4.84 times 10 to the negative 19 joules and divide by 6.63 times 10 to the negative 34 joule seconds, I get a frequency of 7.31 times 10 to the 14 hertz. Now, since we're talking about light, the wavelength of light times the frequency of light equals the speed of light, which is a known constant. So I could approach this by saying my wavelength would be the speed of light divided by that frequency I just calculated, or if I wanted to start with my energy, the wavelength would be Planck's constant times the speed of light divided by the energy. And some folks file away Planck's constant times the speed of light in a couple of different units because there are a number of factors where this comes into play, can make calculating things a little bit easier. However you end up doing this, you end up with a wavelength of 4.1 times 10 to the minus 7 meters, which is 410 nanometers. And we consider ultraviolet to begin at a wavelength of 400 nanometers and smaller. Now, if we go down an energy level to n equals 5, n equals 5 to n equals 2, I take E2, my final level, minus E5, negative 3.402 EV minus negative 0.544 EV gives me an energy of negative 2.85 EV. Again, we're emitting energy. We're emitting energy, if I do the same process, convert that into joules, divide by Planck's constant, I'd get a frequency of 6.90 times 10 to the 14 hertz. So I put my units in hertz per Planck's constant just to make this an actual equal sign here. And there should be a minus sign since it's emitting a photon. Just state it's emitted. And then doing the same thing with my wavelength. My wavelength would be 435 nanometers. Now as I keep working my way down, for n equals 4 to n equals 2, it translates into a frequency of 6.16 times 10 to the 14 hertz, which is a wavelength of about 486 nanometers. And the lowest line, n equals 3 to n equals 2, I get a frequency of 4.56 times 10 to the 14 hertz and a wavelength of about 657 nanometers, which is towards the low end of the red spectrum. Thanks for watching.